Okay, welcome back for Kostyu's third talk on integrability and spin shifts.
Thank you. So last time we were talking about symmetries. If you look at Superangel's theory and strings in AdS 5 crosses 5, then they share the common symmetry group, which is PSU 22/4. On the Superangel side, this is the superconformal group. So it includes supersymmetry transformations, Lorentz group, and conformal transformations. On the string side, this is the isometry group of the corresponding supermanifold, the target supermanifold. Now, since this is the global symmetry group, the Hilbert space carries representations of this group. So any state lies in a certain multiplet of this group. So it has rank 8. Well, it has rank SU2 type group has rank 8, but we put the central charge to 0. So there are seven numbers that characterize any representation. So the spectrum is, mathematically speaking, just a set of admissible representation of the supergroup. So which can be characterized, say, by their highest weights, which can be taken to be the scaling dimension, Lorentz spins, 2 of them, and 3 SO6 spins. And this should be a common spectrum of both theories. So on the Superangel side, this is the spectrum of local gauge invariant operators. So they carry the representation of this group. And on the string side, this is just the spectrum of string states. Now, 5 of these numbers are half integers, so the spins are quantized. But the scaling dimension is a continuous parameter. So in a sense, it is the only interesting label that characterizes the state. And since it is continuous, it can depend on the coupling constant. So we can think of this as an energy and think of the spectrum. So try to find the spectrum of all possible scaling dimensions. So in other words, we want to diagonalize the dilatation operator. Now on the string side, dilatation operator in certain gauge is the string Hamiltonian. Yes.
Why the 5 charges are half integers rather than integers?
Because that depends on normalization. So we normalize spins such that they are half integers. So say the so spin 1/2 is the smallest possible representation. Now the question is, what is the dilatation operator on the gauge theory side? And as a matter of fact, by the AdS CFT correspondence, diagonalization of the dilatation operator. So the dilatation operator should be one and the same object on both sides. So what I will try to describe you in this lecture is how to construct the dilatation operator in perturbation theory, actually just to the leading order, and what we can get from it once it is known. So, so let's start from the second question. So, suppose that we managed to find the set of conformal primary operators. Then we can use symmetry to restrict their correlation functions. And in fact, conformal symmetry is rather restrictive. In particular, the 2-point functions are completely fixed. I'm sure you have heard this many times, this statement, but let me give a sort of formal derivation of this fact. So let's consider a 3-point function of energy momentum tensor and two primary operators, which we will take to be scalars for simplicity. So we consider the following integral. Where the integration is on over y is on the sphere of radius r, and points x and 0 are somewhere in the inside the sphere. So this correlator, of course, should decay at infinity sufficiently fast. So if you take the limit when this sphere goes to the radius of the sphere goes to infinity, this correlator will just vanish. But on the other side, on the other hand, we can integrate, use the Stokes theorem to integrate by parts. So this is, here we have the integral that contains the flux of the dilatation current. So then we can contract the integration contours to small spheres around 0 and around epsilon. So the integral in between vanishes because it contains the divergence of the dilatation current, and the dilatation current is conserved. And then plus the integral around x and around 0 of the same thing. So this term vanishes because the current is conserved. And these two terms describe the variations of the field of this field under conformal transformations. So we can write them using the fact that O is a primary scalar operator. So first of all, we can write them as delta O of x of y of O of 0 minus O of x delta O of 0. And now using the transformation law for the primary operators, you can write that this is equal to x mu d mu plus delta acting on O of x 0 and plus O of x here should be minuses delta O 0. So since the left hand side is 0, we get a differential equation for the correlation function. Now, using also the rotational and translational invariance, we can say that the correlator should only depend on the absolute value of x. So this equation is sufficient, has the unique solution, which tells us that the correlator should behave as as a power of the distance. And so this power is precisely the scaling dimension. Now the constant really doesn't matter because we can always absorb it into normalization of the operators. So once we know the spectrum of scaling dimensions, we immediately know all the two-point functions. So conformal symmetry also restricts three-point functions and higher point functions to a lesser degree. But in the large n limit, two-point functions is the only that we are allowed to calculate, because for single trace operators, the correlator of n traces behaves as 1 over n to the 2 minus n. So all of these higher correlation functions are just suppressed. They are one-variant corrections. Okay, so let's consider an example. And consider the simplest possible operator. It actually has a name to it called Kanish operator. Which is defined as the trace of two scalar fields with their SO6 indices contracted. So this is the most simple operator one can imagine. It's a mass, if you wish, it's a mass operator for the scalar fields. Okay, so since each phi has dimension 1, we expect that the scaling dimension of Kanish operator is 1 plus 1, which is 2. And indeed, if we calculate the correlation function, kx, k0, then, okay, so it's given by this diagram. So this is x, this point is 0. So in the coordinate representation, this is just the product of two propagators. Each propagator is basically 1 over x squared. So what we get is some unessential combinatorial factor, which is, let me write it down exactly. So the combinatorial factor is just 3 lambda squared. So indeed it behaves as some normalization constant divided by x to the 4 as expected. That looks like rather dubious calculation, and in fact this statement that it scales as 1 over to the x to delta is looks like a very shallow statement, because it's just a scale dimensional analysis. We know that phi has dimension 1, so we multiply 4 scalar fields. The right hand side should have dimension 4 in the units of mass, so it should behave as 1 over x to the 4, since we don't have any dimensionful parameters in the game. But if you do a one loop calculation, you discover that things are not that simple. So at one loop there are 4 diagrams that contribute, or sorry, 3 diagrams that contribute. We can insert a scalar vertex. So the scalars can exchange a gluon. Or we can introduce various one-loop self-energy corrections into each of the lines. So I'll not go through the calculation of all these diagrams, but let us concentrate on the first one, which is, I mean, easiest of all of them. So if we write down the expression for this diagram in the coordinate representation, then up to some factor, it is given by the following integral. So it's basically an integral over the intermediate point of x minus u to the 4 times u squared times u to the 4. So there are two propagators between x and u, so this gives a factor 1 over x minus u to the 4. And 2 propagators here, this gives a factor 1 over u to the 4. If you do combinatorics, carefully get this number in front. So, and the crucial point here is that this integral is divergent. So it diverges logarithmically if u approaches either 0 or x. So we need to actually we need to regularize this integral in some way. So this might look strange because n equal 4 Superyoung-Mills is a finite theory. So why do we get divergences? Well, the reason is that once we introduce local operators, they correspond, so they contain products of the fields in the same point, and that may induce new ultraviolet divergences that has to be taken care of. So let's regularize this in some way. And if you are just looking at the dependence on the cutoff, which will turn out to be enough, then it doesn't matter how we regularize because it's a logarithmic divergence. So we can immediately write that it's equal to minus 15 lambda squared over 32 pi to the 6, 1 over 8, 1 over x to the 4. So by looking at dimensions, it's clear that it scales as 1 over x to the 4. And then integration produces logarithm of the UV cutoff precisely with this coefficient. So this is basically, well, it's a very simple calculation. We just concentrate on the vicinity of 0, then multiply the result by 2, but because there are two divergent points. So the coefficient in front of the cutoff is fixed. And then, because there is no other dimensional scale, the cutoff is accompanied by just the distance. And then there is a numerical constant that depends on the way we regularized. It's here. This is lambda cubed. Thank you. Now, if we add all three diagrams, each of them contains ultraviolet divergences, and they don't cancel. So I'll just write down the result of this calculation. So what we find is that the tree-level result is shifted by the logarithm. So this constant really doesn't matter because we can always absorb it in the redefinition of lambda. Okay, so what does it mean? I mean, we proved from very general principles that this correlator should behave as a power as a function of x. And then explicit calculation shows that it depends logarithmically on x. So does this mean that the scale invariance is broken? Well, the answer is not that there is no breaking of conformal symmetry here. But to see this, we need to go to higher loops and calculate the whole series of diagrams that will lead to exponentiation of this logarithm. well, there will be also further corrections. But the important thing that the correlator will be proportional to some constant divided by x to the 4, and then the exponential of this logarithm, which gives a power. So you see that this power actually shifts the scaling dimension. So the once we believe in this exponentiation, the anomalous dimension, the scaling dimension gets a quantum correction, so which is called the anomalous dimension. So the correlator will decay at large distances a little bit faster than we would conclude by looking at tree level. So this is anomalous dimension. So to conclude, there are two effects. So first effect is that normalization constant becomes divergent. So we need to regularize the Feynman integral that we encountered at one loop. And then lambda, after exponentiation, appears as a normalization factor in this correlation function. And also the scaling with x turns out to be a little different. So this means that, the appearance of this normalization factor means that we should renormalize the operator. So the physical operator whose correlation functions are finite differs from the bare operator by some power of the cutoff. So if you from the very beginning would have considered the correlation functions of this operator multiplied by lambda, that would cancel with the cutoff that comes from Feynman diagrams, and correlation function will be finite. So this is just the usual procedure of hiding short distance singularities inside the operator.
Can I ask a question? When you calculate the anomalous dimension to more higher loop order, doesn't the result depend on the regularization scheme?
Not in the conformal theory. In the conformal theory, there is a scheme-dependent definition of what anomalous dimension is. We can look at correlation functions, and their decay exponent defines what the scaling dimension is. So X dependence cannot be scheme dependent. Now, it is true that in non-conformal theories where the notion of anomalous dimensions is also useful, there is sort of no unique way to define them, so they become scheme dependent beyond certain loop order. Yes?
How to actually get this result? Is there something special in the whole perturbation series for this Konishi operator that lets you sum out all the contributions, or is there a more clever way? Because in general it would be very hard to sum up all the contributions.
No, this is a general statement about perturbation theory that you can hide ultraviolet divergences in multiplicative renormalization. So that can be proven. Well, one way is to directly look at how diagrams, combinatorics with the diagrams, and see that everything multiplicatively renormal is multiplicatively renormalizable. So in principle, we could have added this operator to the action, so added small mass to the scalars, and then this would be the coefficient, or the mass would be a coupling constant that would have required renormalization, and basically renormalization factor for the mass is precisely this this factor by which we should multiply the operator.
Was said it's still there are still high loop corrections, right, to anomalous dimensions.
That's right.
So even though we did one loop calculation, but then you said it exponentiates. But as you correctly said,
Yes.
it not only exponentiates, it gets other corrections.
Yes,
So in
that's true.
principle, there is a
So-
plus order lambda squared, lambda cubed. etc.
Absolutely true. So at order lambda squared, because of the exponentiation, we should get logarithm squared with the known coefficient that is consistent with this exponential form, but we'll also get a single logarithm that will be exponentiated by even higher loops. So these coefficients of single logarithms are higher contributions to the anomalous dimension. So the anomalous dimension is a power series in lambda.
We don't have any non-perturbative way of calculating this.
In this particular theory, and from very recently we do certain cases because it's solvable. But in principle, it's an arbitrary complicated function of the coupling constant. So it's as hard as calculating the two-point correlation function. Now, okay, so let's think what we have done here. So basically, the divergence in this diagram comes from those regions of integration where u is either close to here or to here. And this multiplicative renormalization is precisely the extinction of this short distance singularity. So we basically replace an operator, Bayer operator, by something that contains a cloud of virtual particles around it, so that the correlation functions are free from ultraviolet effects. So this should be finite, and basically we replaced the Bayer operator by okay, adding any divergences that it can possibly produce. Now, since all of these divergences are local, and in fact doesn't depend what sits here on with what we couple this operator, so it's just a property of the operator itself. We could have computed 3-point correlation function, and we would find that we need precisely the same counter terms to renormalize it. So to conclude, if we have an operator, then in general we will need to multiply it by some lambda cutoff dependent factor to extinguish possible local divergences. So this factor has to be proportional or actually equal to lambda to some power. And the fact that lambda has dimension of mass. So the reason that we got different dependence on x is that now this explicit appearance of the cutoff changes the counting of dimensions. So we could have thought that k has dimension 2 by just counting the number of fields in it, of number of scalars. But in fact, it contains also lambda to some power. So this means that the total dimension of the operator is its bare dimension delta 0 plus this additional anomalous dimension gamma. And it is this gamma, which is a function of the coupling constant. It is this gamma that enters the correlation functions and determines the way the rate at which they decay at infinity. In fact, this is not. This picture is a little bit oversimplified, because usually we have many operators that are renormalized through each other. In other words, the renormalized operator is in general a linear combination of bare operators. In other words, it's not a priori a simple problem to identify operators that are multiplicatively renormalizable. So in general, the operators will mix. And this mixing can be rather complicated. So in general, the z factor is not a scalar factor, but a matrix. So if we have a set of operators, that we'll label by some index b and a, then the renormalized operators will be linear combinations of them with coefficients that depend on the cutoff. Now, the only restriction on the possible operators that can mix is that they should all have the same quantum numbers, right? Because we cannot mix apples with oranges. And so the operator should have the same charge, the same bare dimension, etc., etc. So in principle, good operators are only those that renormalize multiplicatively. So what we want to do is to diagonalize this matrix. And okay, in perturbation theory, Z is a series in logarithms of lambda. So what we really diagonalizes the mixing matrix, which is defined as z minus 1 dz over d log lambda. So so what we want to do is to find the basis of operators in which this gamma is diagonal. So the eigenstates of the mixing matrix are conformal operators with definite scaling dimensions. So their scaling dimensions are shifted by the eigenvalues. The eigenvalues are obviously the anomalous dimensions. And so the dilatation operator in field theory is basically this mixing matrix up to the term that is tree-level bare dimension. So this is how the dilatation operator arises in field theory. Now, usually for operators like Kanishi, the mixing problem is not very complicated. Well, for Kanishi, there is no other operator it can mix with, so there are no other scalar dimension 2 operators. It will be singlets under SO6. But if you consider more complicated operators, then there are many degenerate operators, and they can mix in a rather complicated way. So perturbation theory for anomalous dimensions is in fact very, very degenerate. So to understand what kind of difficulties we can get, let us consider renormalization of some sufficiently large sector of operators, namely arbitrary scalar operators. So we'll see that their mixing problem is quite complicated. Even at one loop, the mixing matrix can be very large, or it grows very fast with the size of the operator. And what comes to rescue is the spin chain. So the problem can be reformulated in a useful way. And apart from that, in n equal 4, it exhibits wonderful symmetries, namely symmetries associated with integrability, that allows to solve the problem completely, and not even at one loop, but even at higher loops. But what I will be talking about will be mostly the one loop dilatation operator. So let's consider operators that are constructed from L scalars. So we take L scalar fields, multiply them at the same point, and take the trace. So the scalar fields have SO6 indices. So in principle, we can contract them with we can take various linear combinations, which is a tensor with L 6-dimensional indices. So the number of operators is roughly the number of possible tensors with which you contract these indices on the scalars. And actually, the useful interpretation of this object, of this coefficient of various operators, is that associated with the wave function. In the space of all possible operators with the Hilbert space. So I'll call it Hilbert space, although it's of course finite dimensional. So roughly speaking, there are 6 to the L possible states. So each index can have 6 possible can take 6 possible values, and this means that the Hilbert space is basically a product of L copies of R6. Except that we should take into account that the trace is cyclic, so we should factor out cyclic permutations. Right, so the cyclic permutation of indices on the C leads to the same operator. Okay, so this is the Hilbert space, or at least it is some linear space. Then the mixing matrix will be a matrix in the space, so we'll interpret it as an operator. A physically very intuitive way of thinking about this Hilbert space is that it's a Hilbert space of a spin chain. So we have L sites. At each site we can have spin. Well, it can take six possible values here. And the mixing matrix is just a Hamiltonian of the spin chain. So it's probably more intuitive if we consider a subsector of this spin chain. So if we make linear combinations, complex linear combinations of the scalar fields, it's sometimes useful to do that. Then we can consider say operators that are built only of two of these complex scalar fields. So this is called as U2 subsector, and it consists of operators that are products of say Z field and W field, and of course we can take all possible permutations of Z's and W's. They will lead to different operators. So this type of operators, I mean the number of them is roughly speaking 2 to the L. And the Hilbert space is C2 raised to the L power divided by cyclic permutations. So this is, well, literally the Hilbert space of a spin chain. So at each side of the spin chain we have two states, and So here they are z's and w's, but we can equally well denote them by up and down arrows. So we can distribute up and down arrows on a one-dimensional lattice. So say up arrow is z and down arrow is w. Then of course distributions of these arrows are in one-to-one correspondence with all possible operators of this type. So these operators are basically equivalent to words in the alphabet with 2 letters, and this is the same as the Hilbert space of this spin chain with normal spins that can take 2 values up and down. So now let's calculate what the mixing matrix is for these operators. So for that we can consider some correlation function of such an operator. It doesn't matter what particular correlation function we consider, because one and the same z factor removes all the divergences from all correlation functions. So what kind of diagrams can we get at one loop? Let me draw them as single lines, but here it is important that we are doing the large end limit, and so just you should think of this as double lines. Now it is possible to so the lowest corrections is the gluon exchange. Well, they're basically the same as in this calculation of Kanish operator. Then self-energy. Then we can insert the scalar vertex. And actually that's it. Now, 2 important points here is that in each of these diagrams we only only 2 of the scalar lines are involved, the rest are just spectators. So we can concentrate only on this part of the diagram. It's the only part that can produce divergences. So the mixing matrix acts only on 2 of the indices here. It picks up 2 indices of the scalar fields and mixes them in a certain way. Now the second important point is that only nearest neighbors can interact, and this is a consequence of planarity, because the diagram where we cross intermediate lines are all 1 over n suppressed. So if you draw it in double line notations, it becomes probably more obvious. But okay, so it's clear that we cannot connect these 2 lines without crossing the intermediate ones, and so we can draw this diagram without self-intersections in a plane. So it will be 1 over n suppressed. so just from that we can see that the one-loop mixing matrix has a very peculiar structure. It will contain interaction only of nearest neighbor lines. So this local Hamiltonian is basically acts on a pair of indices of the two scalar fields. So H L plus 1 acts from R6L cross R6L plus 1 into itself. So it is 36 by 36 matrix, but it's also SO6 invariant. So in fact, there are only three possible structures, three possible index structures that can arise. So it's a matrix with 4 indices. Well, if you start, it crosses 2 scalar lines, so that can interact in the middle. So suppose that we start with indices I and J. Then after interaction, they go into indices I prime, J prime. There are basically three SO6 invariant combinations of these indices. So one possibility is that I prime is equal to I and J prime is equal to J. This means that in terms of SO6 structure, nothing happened. So we can think of this as the Bayer operator, and this is renormalized operator. So once we get this structure, this means that it doesn't lead to any mixing. Now I prime can be also equal to J and J prime to I. So this is permutation. So let's introduce a special name for it. To define operator that acts in this space by permuting the indices. So if you take tensor product of two vectors, it will just interchange them. And we also can get a trace operator in which the primed indices and unprimed indices are contracted. So this is the trace operator. That's denoted by K. And so this local Hamiltonian is a linear combination of these three structures. It's a relatively simple calculation to fix all the coefficients. Just need to do some simple one-loop diagrams. I'll just give you the result. the result is that h is equal to 2 plus k minus 2p. So all three structures appear with various coefficients. So graphically we can denote them like that. So this coefficient is a unit matrix, 2 plus then the trace and plus permutation, minus 2 permutations. So this just shows the flow of SO6 indices. Yes?
These creators appear as a sort of contraction in the Feynman diagram.
Yes. So just one takes the Lagrangian, inserts all possible vertices, and
This is very particular from the N equal 4.
this is very particular for
Interaction
equal
then.
4 interaction. Yes.
Okay, you say that you have these four, this trace of four operators, phi, and then the contraction gives this this form.
Yes.
Do you have any reason to expect that these are integers, coefficients?
Let's see. Well, at higher loops they are not integers, but well, this is because the diagrams are so simple. So yeah, basically the only non-trivial contribution comes from the same diagram that appeared in this Kanishi calculation. So with this normalization, it has to be integer. But if one goes to higher loops, there is some structure. So for instance, at 2 loops, they are integers in particular normalization. At 3 loops, they are also integers, but then at 4 loops, suddenly there is a zeta of 3 that appears.
But these integers that you find, can you get them from some combinatorial reasoning?
Okay, for one thing, they are consistent with integrability. So the remarkable fact is that this Hamiltonian is integrable, and the ratio of these two coefficients is crucial for that. So it's only this Hamiltonian that's integrable. And it seems that, actually integrability imposes some constraints, but it does not really require that all of them should be integers. So it
Is there a constraint that it has some zero eigenvalue?
yes, there is such a constraint. It's I'll just explain what are these what are the zero eigenstates in moment. Okay, but first let me say a few words about integrability. Or, no, actually, I'd rather do some examples first. So example number 1 is the Kanishi operator. So Kanishi operator corresponds to the chain with 2 sides. And we contract indices of the vector sitting with these sides. So the wave function C ij is just delta ij. Right? So let's take this one loop mixing matrix and hit this wave function by it. So now permutation operator, well, there are only two sides, so but there are two links actually, so we should act by the same operator twice. So operator, let me say this. So the operator acts on each of the links on this lattice, and then we should sum over all possible links, and this is how it acts. So permutation it evidently leaves this state invariant, because if we permute the indices, nothing changes. Trace well, produces a factor of 6, right? Because we just contract the indices on the delta function. So this gives the anomalous dimension of Kanish operator. That's lambda over 16 pi squared. And then, okay, so you see that once so the coefficients between the unit operator and permutation are opposite. So if the eigenvalue of permutation is 1, these two terms cancel. The trace operator gives 6, and we should multiply by 2 for the two links of the lattice. So we get 3 lambda over 4 pi squared. So this is precisely the anomalous dimension that we get from that two-point function. The second example. What?
Just one question.
Yes.
About the C that you just erased, that define your operators.
Okay.
So that was the wave function that you called.
Yes, the CI.
Right, exactly.
Yes.
So do you exclude the ones that correspond to the BPS operators?
No.
And you include those?
I include those, and I was about to discuss the BPS operators.
Okay.
So I would actually call them chiral primary operators. Well, indeed, they are BPS. They are sort of lowest components of short multiplets of this large supersymmetry algebra. So they are protected from getting quantum corrections. And let's see how it is reflected in this dilatation operator. So chiral primary operator has the wave function that's symmetric and traceless. And this is precisely the conditions that annihilate this Hamiltonian, right? Because, okay, if we hit by the trace operator because of tracelessness, so tracelessness means that if you contract any pair of indices, the C vanishes. So this means that the trace operator acts trivially, and the permutation operator, saying that the operator is invariant under permutations is the same as saying that its wave function is symmetric. So so this gives 0, and then permutation does nothing. So this means that the anomalous dimension of chiral primary operators is 0, and this is true to all orders. Okay, I think I'll stop here and I'll talk about integrability in the next lecture.
Do we have questions? Yes.
You said that the eigenvalues of the Hamiltonian give us the formula we need for correction to the formula. What
Yes.
does that mean, the eigenvectors?
Eigenvectors are conformal operators, so it's the only sensical operators that one can build because okay, so they have definite dimensions. Yes,
If you take all 6 scalars, do they mix into other fields?
they do, but at higher loops. So yeah, that's true. This sector is only closed at the one loop level. Yes.
So as you said, the spectrum of dimensions on the gauge theory side corresponds like to string energies, right? On
Yes.
the string side. So, however, there should be some explicit prescription, like in the case of BPS operators, how to compute the 2-point functions from string theory, the 2-point function of the gauge theory. So, is such a prescription known for non-BPS operators?
Yeah, prescription is generic. So you know how to, once you know the mass of the corresponding string state, you know what the anomalous dimension is. So for scalars, it's, I think there is this famous square root formula is, I forgot, it's n plus squared minus 4, something like that. I'm afraid to don't take this formula too literally, but there is some relationship between the mass of the string state and the dimension of the corresponding operator. And the only problem is that we don't know the spectrum of masses for the string. So that it's not known how to quantize string theory in this background. So we know that it has some massless state because states that are protected. But we can't tell what is the spectrum of the massive states, except for some regions where these states are semi-classical or very heavy.
Any more questions? Let's posture again.